Ohayou gozaimasu. So before I begin, I just wanted to say that I feel deeply honored to be here speaking at RubyKaigi. This is my first time in Kyoto, my first time in Japan, actually. I asked Jonan if I needed to wear a special gaijin hat to identify myself easily, but he assured me, for some reason, I wouldn't need it. So I've always wanted to visit here and attend this great conference, let alone be welcome to speak at it. So thank you to Matsuda-san and the rest of the RubyKaigi organizers and to my employer for giving me the time to come here. So who am I? My name is Chris Arcand. I look like that on the Twitter and the GitHub. And my username is all the same everywhere. I'm from Minnesota in the United States, next to the Canadian border. Minnesota is lovely. It looks a lot like that. I live in the metropolitan center of it, the Twin Cities. The Twin Cities are two major U.S. cities that are called Minneapolis and St. Paul. They're about 13 kilometers apart, which isn't very common in the U.S. because two downtown areas so close to one another just is not common. We have absolutely gorgeous summers there and have beautiful forests and lakes to enjoy. In the winter, we love playing ice hockey, and the winters always look as beautiful as the picture down here at the bottom. Except, if you've been there, you know that I'm actually lying. Winters look a lot like this. That's a man on a snow bicycle with big fat tires to have traction, riding through a blizzard. And after such a blizzard, sometimes things will look a lot like this. This is a street of cars parked that are completely buried in snow. But I'm just going to repeat that the summers are lovely, and you should at least come visit during the summertime if you're nearby. So I'm a Ruby developer at what Aaron Patterson has always described as a small startup. You might have heard of us. We're called Red Hat. I work remotely out of Minnesota. There's no engineering office there. At Red Hat, I work on ManageIQ. ManageIQ is an open source cloud management platform that powers Red Hat CloudForms. It basically aggregates all of your enterprise infrastructure into one place and adds a bunch of functionality on top of it. The code base is hosted on GitHub. It's really easy to find, and you can learn even more about it chatting with me afterward or on manageiq.org. And we're always on the lookout for good developers. If you're interested in joining us, please see me, send me an email, whatever. So why am I here? I am here because I love programming. As you can bet, that means that I love writing code. However, there's something else that I love even more, and that is I love deleting code. So Ruby has been a successful programming language for some time now, and we as Ruby developers might now maintain legacy applications that have been developed on for many years. A consequence of our long-term success is that these applications may contain unused, obsolete, and unnecessary code. I'm going to tackle a very specific case today. I'm going to talk about methods that stand worthless and dead, unused by any callers in the application. This might be fine for frameworks where the public API is never called within the framework itself, but in terms of an application, it just adds cruft. Now, how does code like this end up in our projects? A couple reasons that I can think of. Think of like a developer from the very, very beginning of your project. He might add a bunch of methods that he thinks will be useful someday, but actually aren't and never do become so. They never get used, the implementation might change underneath them, and they don't actually work anymore. It's a type of over-engineering, right? Another one is just poorly written code. Imagine like a brand new, inexperienced developer joins your project. They might write a very specific method that isn't very flexible and is completely unhelpful beyond anything besides that one single spot. Maybe it's one tiny bug, one tiny case. So hopefully these two examples are just caught in code review, but sometimes they aren't, right? And it could be that things have just been refactored over time and the methods just aren't needed anymore. So you might ask, who cares? The short answer is that unnecessary code is confusing. It adds complexity where there shouldn't be any, and it creates an unnecessary maintenance burden on future developers. And it makes you scroll more in your text editor, which is really annoying. But don't take my word for it. Other people think so too. There's a great post by Ned Batchelder called Deleting Code from 2002. In this post, there's a snippet that I'd like to share. If you have a chunk of code you don't need anymore, there's one big reason to delete it for real rather than leaving it in a disabled state: to reduce noise and uncertainty. Some of the worst enemies a developer has are noise or uncertainty in his code because they prevent him from working with it effectively in the future. So before we get wound up trying to implement a feature and already lost in the noise and uncertainty, I ask, What if we could programmatically find unused code to delete ahead of time, before we're trying to implement something else in that area of the code? Well, it turns out we can, to an extent. Today I'm going to describe how a static code analyzer can be built to find potentially uncalled methods. Now, because Ruby is a dynamic, duck-typed language, and this analyzer is only static, it's not going to be 100% accurate. But it has the potential to point out some areas in our code that we can clear the cruft and add a bunch of deletions to our GitHub stats. So we start with some Ruby code that we want to analyze. The first thing we need to do is transform the code to some data structure that we can reason with, which brings us to part one, parsing the code. Now, some of you here know very well how language parsing works and very aware of how it works in Ruby. Some of you might not be so familiar. So I think it's important for everyone to understand how things work from the ground up. So this is a really high-level overview of how general language parsing works from a grammar. So do you understand the following sequences of characters, and how do you know? The boy owns a dog. Okay. The dog loves the boy. Loves boy, though. How could you programmatically determine which of those correct and which are not? Well, there's a way to do it. I'm going to throw a couple definitions that may be very familiar to you. The first is a context-free grammar, or a CFG. It's basically a set of rules that describe all the possible strings within the language. It answers the question, which sentences are in the language and which are not. The other one is Bacchus-Naur form, BNF. This is just one of the two main notation techniques for notating that context-free grammar. So here's a BNF grammar for some of the sentences that we just saw. It might look a little confusing, but it's not. It's very easy. So every word you see up here is a symbol. And symbols are divided into two groups, the non-terminals, which are denoted by the brackets right there. And the other one are the capitals, the terminals there. And the way it works is that a symbol on the left is replaced with an expression on the right between the definitional operator, this : equals. And there's also a logical or at the bottom. So you can choose between owns, loves, or bytes as far as that terminal. So an expression can be a combination of non-terminals or terminals. A non-terminal is always replaced via some rule. And terminals are the actual token found within the language. They terminate at that point. That's why they're called terminals. So let's try that first example. Let's look at the sequence of characters. Now notice I didn't say sentences before, right? I just said sequence of characters. The reason for that is because we don't actually know if this thing is a sentence yet. But there's a rule for that, and we can try to apply it. So if this is truly a sentence, that means it has to be a subject followed by a predicate. Well, we can try and pick a subject as the boy and a predicate as owns the dog. Now, if this, the boy, is a subject, it has to be an article followed by a noun. We can try the as an article and boy as a noun, and we can see that there's rules for article and noun. Now, if this is truly an article, it has to be the terminal the or a, which it is. We found one. And if this is a noun, it has to be boy or dog. We found it. You can also parse out the other side until you find the terminals there as well. So in the end, we've identified every part of what we call a sentence. And if you do a little bit of rearranging, you can see that it creates a tree. Now this is a parse tree. It's a discrete representation of our language that can be used to reason about the sentence. Let's try the other one. The dog loves the boy. Now I'm not going to parse it all out for you, but if you notice the sentence structure is exactly the same, so it works out well. Now what about loves boy though? As you might imagine, it doesn't work. And the reason why is because if that's a sentence and it begins with a subject, and a subject begins with an article, and an article is either the or a, with an R grammar at least, loves is not the or a, so it's a syntax error. It's not found within the language at all. So in programming terms, the first two work, and the third one is an error. It doesn't make sense. It's not found within the language. It has no meaning. So what does this have to do with Ruby? Well, you can ask Ruby the same question. How does Ruby know the meaning of these characters? How does Ruby know that this is a class definition with two method definitions in it, the initialize method with a name parameter? Now, my English examples were easy because we skipped lexing, tokenization, and actual programmatic parsing, but hopefully it captured the high-level essence of parse trees for you. It's a bit more complex in how Ruby actually accomplishes it, but this is what Ruby does. It takes in the parse.y grammar file, puts it into Bison, which is the parser generator, and the resulting parse code is used to take your Ruby code, tokenize it into tokens, parse that into an abstract syntax tree, and that's eventually compiled and made into your virtual machine instructions. So the parser generator from Bison is what's called an LALR1 parser. I'm not going to describe how an LALR parser really works for you today because it's a bit out of scope, but I'm going to plug this excellent book. So the diagram I just showed you from this book, from the slide there, is from this book called Ruby Under a Microscope. It's by a fantastic human being by the name of Pat Shaughnessy, and in it he explains all about Ruby internals. The first chapter is all about tokenization and parsing, and it also includes an in-depth explanation of the LALR parse algorithm, so you should definitely go check it out. So that's how Ruby does it. How are we going to do it? We're going to do it a little differently. We're going to make use of a gem that you might have heard before called Ruby Parser. It is a Ruby parser written in Ruby, and it uses rack under the covers as a dependency. The dependency rack is an LALR1 parser generator, just like what Ruby does. So let's look at an example. We have a class person with one method definition, takes in a name and says, hello name. So you can initialize a new person, and you can say, hello RubyKaigi. If we throw that in an example, and go in a terminal here, we can call Ruby Parser's forCurrentRuby method, which returns an instance of Ruby Parser for that particular grammar, whichever running version of Ruby you have right now. And the instance has a parse method. You can read in the file and parse it. So the thing that's output is an S expression, or a sexp. It's a notation for nested list data, and it originally comes from Lisp. So nested list data is tree structured. This is the perfect notation for describing parse trees. So awesome. This data contains the structure of our code. You can see the block up there is the top level context. There's a class definition called person that has a method definition node called greet with an argument called name, a call to puts, etc. You can see how that works. So now that we have a parser to put our code in a format we can work with, we need a way to process it, which brings us to part 2, processing the S expression. So before we do something really useful with our sexp, we need a way to easily manipulate it and start getting some general information that we care about. Information like finding where exactly methods are defined and in which classes. So we're going to begin to process everything by building a very minimal, tiny class called minimal sexp processor. And the goal of this class is simply to run dispatch, calling a method given a node type in our S expression if it exists. So in our initialize method, we'll build a sort of dispatch hash. We'll take the public methods in this interface, find all of those that start with the prefix process underscore, and then key them within a hash according to their suffix. So that is, if we had a method named process definition, we would seek out the method from its prefix, take the suffix, and place the method name as a symbol within the processor's hash, keyed by that suffix. Now note that the name corresponds to a node type in our sexp. Next, we'll write the main method for our processor. It's called process. Every node in the tree will be passed into this method. It simply looks into the processor hash to call the correct processor method given the current expression's node type. If there isn't one, we just call a default method that maybe we can pass in as an option. If we don't have a method to call and didn't set a default, let's just return nil. Also, we'll put a cute little warning output to say that, hey, if we didn't recognize the node type being processed, we're going to call this default, we're going to warn that we're calling a default method, if that's really what we're doing. So this class, if you noticed, by itself is pretty worthless. There are no processors, but this is simply meant to be a base class. So to demonstrate an example of a processor subclass, I'm going to define a subclass called silly processor. Within our silly processor, we'll define two processor methods. If we encounter a method definition in the expression, process definition will be called. Process not definition will be the method that we'll set as a default for all other node types. Now, the methods just call puts to tell us some information about the node. So if we encounter a method definition, we'll say, hey, processing a method definition node with the method name. And for everything else, we'll just say, hey, we're processing this node with this particular node type. Now, both of these methods call some method called process until empty, right? And we'll look at that one now. So process until empty iteratively shifts and calls process on the next node in the expression until the expression is empty. Every processor method calls this in the end to start parsing the next node. Lastly, we'll fill out our initialize method to call super in the parent first and then set some options that we want. So in this case, we're going to say, hey, if you don't know how to process a particular node, you're going to call process not definition. And we're going to turn off warning about calling that because most of them will probably call that anyway. So there is our silly processor. If we put that in an example, we can do the same sort of thing, get an instance of Ruby parser, make a sexp, and then process that. And it outputs pretty much what you would expect. It's just calling, hey, I see the block node, I see the class node. Oh, here's a method definition node. It's called greet, and then processes everything else. Now, this might seem rather pointless, and that's because it is. But it demonstrates that we've now added the next tool to our tool belt. Now we're at the point that we can run whatever code we want at a given node. And this allows us to build more complex things like, say, a method tracking processor. So using some information from Ruby parser, we can now record where we see method definitions in their classes and their line number. Setting this up, we're going to use the same options as our silly processor, but there's a few new things. You can see there's a class stack and a method stack, which are just initialized as empty arrays. And there's also a method locations hash. And what we're going to do with that is we're going to populate it with the method signature as keys and the file name and line number as values. And the file name and line number will be taken from Ruby parser directly. Next, we're going to write out our process methods. The first one, process definition, is just going to shift off the node type, off the expression, and find the name. It's going to call this thing called inMethod, that we'll show in a minute, and then just process everything in that definition until empty. Process class, same sort of thing. It's just going to call inClass instead of inMethod. And then lastly, the process until empty I had showed you earlier. So the two location methods that actually do the work, as I said, are inMethod and inClass. Now, hopefully you can see that, but it's very simple. They both just add the current method or class to their respective stacks and pop them off once we yield to the block passed in. So with inMethod, we also record the current method signature in our method locations hash with its location. Now, the other thing is that, think about it, as you enter a new class, that's a new method space, right? You might have methods defined in and out of that class. So what we do is when we enter a new class, we give it a new method stack. We're going to save the old stack, use a new one for that class context, and then revert back to the old stack when we're done processing the class. Lastly, we have a couple little helper methods. So the current class name is just the first class name in the stack. The current method name is just the first method name in the stack. And the signature we're going to say is the signatures that you're used to seeing, class with a little hash symbol and the method name. So there we go. Let's give that a try. So we're going to expand on our example a little bit. Our person class, we're going to add a little say goodbye, which is pretty much exactly the same thing. We have a new class called dog, which has a method called bark. That's it as far as we add. The things to pay attention to are where the method definitions are. So there's a method on line 2, 6, and 12. So if we throw that in a demo and we pretty print the method locations after processing, it looks a lot like this. Person greet is in example2.rb, line 2. Say goodbye is on line 6, and bark is on line 12. So awesome. We now have where methods are defined. So the generic processors that we've built so far to process the S expression tree and record method locations provide the footing with which we can build our tool on. The only thing we need to do now is process the call nodes within the tree, see what's being called, and then line them up with what callees we're now tracking. Which brings us to part 3, building the dead method finder. Okay, so we finally reached the point where we can build the dead method finder we've been working towards. Let's say a class called dead method finder, which will subclass from our method tracking processor that we had just built. We're going to maintain 2 very important collections. So known, we're going to say, is a hash containing sets. And we'll use this to maintain a mapping of method names to the set of classes that define them. Called, we'll say, is just a set of methods that were called. We'll write out our two processor methods. So process definition, we're going to key into the known hash, adding the current class name being process to the set of classes that call this method, and then just call process until empty on the remaining sexp nodes. And for process call, we're just going to add the method being called to the set of called methods. So next we'll define an uncalled method. This is where we'll take the difference between known and called methods, in other words, the ones that aren't being called. For each uncalled method, we then key into the known hash to find where a method by that name is defined, by class and line number. And we also have a little helper method called plain method name, and that's just because the method name for Ruby parser is a string in a certain format, but we're going to use symbols to do comparisons. There we go. Let's give that a try. So we're going to expand our example just a little bit further. We're going to say, instead of greet and say goodbye, just calling puts, let's have it use a helper method called speak. We're going to add a pet dog that takes in a supposed dog object and sends it the method pet. And with our dog class, we're going to add an attr accessor called fed, because, hey, maybe you need a Boolean to know whether or not you fed the dog. And also another method called pet and dog. So we're going to add a little bit of realism. We're going to use some names. I'll be the person, and I have a dog. His name is Ruben. We'll say he's the dog. So I'll greet RubyKaigi, Ruben will bark, and then I'll pet Ruben. Notice that say goodbye is never used down here. And fed, none of those two methods, the getter or the writer, are used. All right. So if we puts the processor.uncalled after processing it, we get this little hash down here. It says that, okay, say goodbye in the person class and pet in the dog class are not used. Well, this is not right. This guy right here, remember we said, hey, I have a method called pet dog where I pet the dog. It's used in there. It's being used by another method somewhere. It's not a dead method, right? Well, if we look at the S expression, we can see what the issue is. So this is saying, hey, method call to send on the dog, sending it a string, a literal symbol of pet. So the problem with this is that our process call is using send as the method being called, which it is. It is using send. The thing is, we want to take into account that sending implies a method call directly. In other words, we've hit an edge case, right? Now looking at the expression, we can find where the actual method being called is, which is the argument, and add some logic to say that that is the method being called and handle the edge case. We'll say, hey, when we process a call, if the method name is send, public send, or underscore underscore send, underscore underscore, we're going to just add that argument to the called hash instead and process until empty. All right. We give it a try again, and it turns out that's being used as a call node, so it doesn't show up in our output. So that's great, but it's still not correct. This guy up here, attr accessor fed, this is never actually used, right? It could be fed or fed equals. If we look at our S expression, we can realize that attr accessor is itself a method call that defines methods, the getter and the setter, which is why our method tracking processor doesn't find them. So we add another edge case in our processor to handle that. When the method name is attr accessor, we can go through and record that method name and the method name equals as a known method. So record known method is just a little abstraction that we made, helper method that we made, that does the same thing that we were doing in our process definition method, except it double checks that the method location was properly recorded. So while we're here tinkering, let's also pretty up that output into something a little more readable. Let's define a method called report that looks through the uncalled methods. For each of them, let's look up the location of that method via the method locations hash in our parent class, throw all of that into pretty formatted lines to report, compact it for posterity, and skip this class if there are no uncalled methods. And if there are, we join it all together and print it out. So processing the code now is just getting the S expression, processing it, and calling report. And here's what the output looks like after we've fixed the attr accessor case and prettied up our output. So awesome. We have person say goodbye, example2.rb line 7 right there, and dog, fed and fed equals, both defined right there. Now remember, that this static analysis tool is not always 100% accurate, and these are potentially uncalled. So we should still do some manual checking ourselves to be a little more certain that these really are deletable. As suspected, it looks like they are deletable in this very, very easy example. Doesn't it feel great? Isn't deleting code fun? So we're done, right? We made a dead method finder. Now we can start finding code to potentially delete left and right. It's time to open a dozen new pull requests and to add a bunch of deletions, right? Are we truly done? No, we're not done. Ruby is complex to parse, at least, right? The good news is that adding edge cases is easy. So let's look at that attr accessor fed again, right? We'll say Ruben.fed equals true. Ruben is my dog. If we add that to the code here, you'll notice that it's still marked as being called here. Now, if my dog were here and saw that him being fed was an issue, he would probably just say, deal with it, right? That is an actual picture of my dog wearing sunglasses. I sometimes call him Ruby because his name, or whatever. Okay. Anyways, let's fix that edge case. So this is an attribute assignment node, right? It's just a node that we haven't parsed yet, right? We haven't processed it yet. And it's very easy. We're just going to say, hey, if it's an attribute assignment of Ruben and the method name being called is right there, we're going to say that that is a method call. And we just add it to the called set again, right? Run it again, and we find out that it does actually work. Perfect. Now, there's so many more edge cases. What about Rails methods? So every bit of Rails DSL and controllers and models that you're used to using would be an edge case. And there's a lot of them. Think about it. There's after commit, before create, after create, before update, before destroy, before filter. It's not called before filter. It's called before action now. There's around save. There's validate. There's validates. There's validates length of. There's after validation. There's validates format of. There's validates cuteness of. There's validates confirmation of. There's a lot of stuff to go over, right? And what about my own DSL? So in ManageIQ, we actually have our own virtual column implementation for active record. This digs deep into active record internals to allow us to treat any method as a database column, amongst other things. It's mainly used for reporting purposes, reporting attributes of entire tables with extra attributes sprinkled in. So we actually added DSL to Rails models in the form of virtual column calls. You might have a class called disk that might have many partitions, and we'll say that a virtual column allocated space of type integer uses all of those partitions. Now, my point here is just that this DSL and Rails DSL calls aren't that difficult to handle. It's just another edge case. All of these methods look essentially the same, right? Most of the time, it's just arguments of symbols naming methods to be called, right? I'm not going to go over each little bit, but it's the same sort of thing. We can keep a collection of everything that we would expect, take all those symbols, and put them into the called set. My point here is just that as with most things, with the right tools, the job is not very difficult. Customization is easy. Another thing that's really easy is that you can execute this code on your project right now. There is a Ruby gem called debride. So to debride something is to remove dead, contaminated, or adherent tissue and or foreign material. When I first had the thought of programmatically finding dead code, I went down the same path that we just did, starting with rack and Ruby parser. I then discovered the lovely simplicity of processing S expressions with a gem called sexp processor. It was created to easily do generic processing of the S expressions given by Ruby parser. It's actually comes from parsetree if you used that before. It also provides a method-based sexp processor to do the method and class tracking we did with our method tracking processor today. I then, to my great delight, stumbled on debride, which does exactly what we just did today with our dead method finder. What's more is that everything you see up on this stack from Ruby Parser on is written by the same person. Each one of these projects is written by Ryan Davis and the Seattle Ruby Brigade, some of which I know are back there. I see them. I have been hacking on debride off and on for the past several months, customizing it for ManageIQ and finding crufty code to delete on a project that started in Rails 1.2.3 nearly a decade ago, and I thought it'd be fun to rebuild the basic concepts for you today. So all of the code you've seen is a modified and minimalist example of ZenSpider's very excellent work. So what does debride provide for you that we haven't covered today? Well, it covers more edge cases, first of all. Our simple method tracking processor and dead method finder are the core of what debride does, but there's much more to consider. What about class methods with def self.methodName? What about defining methods on a singleton class? There are many cases yet to be handled. It also adds all sorts of lovely little options like, hey, I want to exclude certain files. I want to whitelist a particular pattern for methods that I know definitely are called. Maybe you want to focus on a particular path or enable Rails mode, which looks exactly like you just saw. So I mentioned that I've been hacking on Debride to find even more dead code. Besides adding your own DSL, whitelisting patterns and all that, you can easily do something like this to find other criteria for what might be deletable code. So remember what I said about methods that might be much too context specific, that only have one particular caller? Well, here's a hack to find those methods. Instead of a set, we'll say that call it as a hash, keeping track of method names with a particular counter. And each time we process a call node, we'll just increment that counter. And then all the ones that are called once are just all of the called methods with only one call. Now, it could be that a method is totally fine just having only one call. It's a properly written method. But I found that it's very easy to be able to look through these and find ones that might be just too specific and can be rewritten in a better way or just deleted and something else can be used. So some future considerations. I've been busy enough hacking and deleting code that I haven't refined it enough for it to be worthy of pushing upstream some of the work that I've done. So my future consideration, at least right now, is just actually pushing some of the work I've done upstream. I found a couple little bugs and cleanup and whatnot. But wait, there's more. Remember that tools like this are but one tool in the toolbox when finding ways to clean up your code base. Today we looked at one way, parsing and statically analyzing Ruby itself to find potentially uncalled code. There's so many other awesome tools to be used in combination. For example, Tom Copeland has Old Code Finder, which is basically a gem that looks through code content line by line by date and authorship. And it tries to find patterns in, hey, this chunk of code is really, really old. You should maybe take a look at it. And hey, that chunk of code is written by, say, a person named Fred. And that person maybe left the company 6 years ago or something. So maybe you should look at his particular bits of code to see if there's anything else that you can possibly remove. It was also unused by Josh Clayton. Thanks, Juanito. This is a really cool project that I haven't even looked at yet. It's written by Josh Clayton from Thoughtbot. It's written in Haskell, and it utilizes C tags to find statically unused code. And it can use anything because it's implemented with C tags, and I love C tags, so I'm really excited to dig into that myself. So before I go, here's a parting message for you. Now, if you used MERB before it was merged into Rails, you might recognize this. No code is faster, has fewer bugs, is easier to understand, and is more maintainable than no code at all. So when you go home, delete some code. It feels wonderful. Domo arigato. Thank you.
Thank you, Chris. I am sure that people have lots of questions for you, and as it turns out, we have time, even though it seems we may not. The other room is about 10 minutes late, so we're going to ask some questions, if that's all right with you. 誰か質問がある人、ちょっと時間がありますので、質問があったらぜひ来てください。はい。
Thank you for your great talk and tool. And I got one question. So from current architecture, is it possible to detect a calling cycle, which means if method foo call method bar, and method bar call back to method foo, but no other method had called them at all? Is it possible to detect this case?
Could you repeat that one more time? I think I'm getting it, but I want to make sure that I got it right.
I'll say again. If method A call method B, and method B call method A, but no other methods have ever called them at all.
I see. I gotcha. Yeah, that's right. So the question is, hey, if you have a coupled thing where there might be like two methods that don't actually do anything in the project that call each other, that would be counted in this case as a used method. And the answer is no right now because it's considered that. That's kind of one of the things that I'm pointing out with the call tracking that I showed you at the very end there. Because an example like that would be found in that sort of hack, right? You would see that, hey, this is only called once. And then when you actually looked at it, you can see, oh, that thing is also only like, you can find that case exactly. So I think it would be really interesting if we added to Debride or any tool like it, the ability to be able to find those cases separately. So you might have uncalled methods and then ones that have like a certain factor of like a certain grade, I guess, for whether or not that might be uncalled. So yes, very cool question.
Thank you.
Yeah. So thank you for the presentation. So how are you doing with the action methods of Rails controllers? There are usually no explicit goals to the actions, but they are usually used or maybe not used.
Sorry, could be that one more time. I'm super sorry. Go ahead.
Yeah. How do you find unused method? Unused action methods of Rails controllers?
Well, it's the same sort of thing, right? You have a node call. So you'd find that, like the DSL example I gave earlier, you would see something like before filter on some method, right? You would register that as an actual method call and see that the method name passed to before filter is a called method, and that would flag it as to whether or not it's actually called. I hope that answers your question. Is that right?
I might be able to answer that question.
Go ahead.
Is this working?
Yeah.
Okay. There's a gem called traceroute, which looks at whether there's a one-to-one mapping between routing that's declared in the routes.rb file and the actions in the controller file. I think it's by Akira Matsuda or something, or someone.
I've heard of it. Mm-hmm. Yeah, I have heard of that. So really, so the question that you asked is basically, hey, can we find out if a controller method is uncalled based on like a routes file, for example, right? Well, the answer is I don't actually know. I don't think RubyParse or Bride actually does that, but it's the same sort of thing, right? You could theoretically do that. And I think I do actually know that Matsuda-san's gem that might do that. Yeah.
Yeah, thanks.
When it comes to uncalled code, often what's happened is that there's an existing method and it used to be called by other methods, and then after a while we deleted that code without deleting the method itself.
That's right.
And by the way, are you familiar with git bisect?
Yes.
Okay. Is there any way of combining git bisect with the class and method name that you're interested in, and try to get git bisect to identify for you when that method was no longer being used?
Yeah, I don't see why not. I mean, so the way that I look back in the history, as I said, so like ManageIQ is a very old Rails app, huge amount of code, and I'm deleting methods that might be 8 years old. I mean, who knows? So I have to be able to look back through the history, and there's a couple little git aliases and whatnot that I use. There's log has a G option, I think it is, for bringing in regular expressions. So you can then look back at the history and have a nice scrolled output of how that method call might have changed over time. And you can very vividly see, like, okay, here's where this method was removed at this such and such a time. And if you keep scrolling down, you can see, oh, this is where this method was actually added. You can see every time that method has changed with Git. So I don't actually see why you couldn't do that. To be able to look through and say, okay, so we parsed through and found a method definition that was deleted. Can we go through the history and make sure that maybe there wasn't a certain number of calls to that method? Maybe those were removed, something like that. It's all static, so you could try and do that and find potentially.
Okay. Yeah, what I was really meaning was running git bisect with the tool that you've created, and have it directly identify which commit caused it to fail the analysis by having a method that exists but no calls to it for that very specific method.
Yeah, so I'm trying to figure out.
So have I explained it well, the question well?
You probably have, but I'm trying to understand exactly. So you're saying that you want to be able to hook up like something like Debride to get bisect to run on each commit to see Okay, I can see what you're saying. So you can run it through.
Pass in the class name and the method name, and GetByte will either say this class name method name is okay, or class main method name is no longer okay, and then get to the commit where the previous commit was fine, but the current commit is no longer fine for that specific class and method.
Yeah, I mean, I don't see why you couldn't really. It sounds like you are ready to make your own pull request for it. That's an excellent idea, for sure. I hadn't even thought about that, and that is something that I feel like would be really valuable. So,
cool.
Thanks for that. Yeah.
Thank you.
Thank you.
So you used the gem for your production code, right?
Yes.
And so how many times did you delete the code which should not be deleted? And how do you think that the tool helps you to avoid that pitfall?
Well, the answer to that is maybe more times than people would like. No, actually, it's not too hard. So the most edge cases because I said that Ruby, as you know, is a very dynamic language, and you can call methods in really weird ways, right? You can call methods where you're interpolating a string and then sending that to send and stuff like that. And obviously, all of those edge cases are pretty much impossible to be 100% correct about. So yes, there have been times where I have removed something. Fortunately, using some of the tools that I just explained with my Git aliases, that you can look through the history and see oh, this method was created here and we removed it here. Most of the time in code review, my coworkers will be able to look through, and there have been times where someone has said, "Oh, it's actually used here. You don't want to remove that." So, but it hasn't really ever been a problem where we actually merge something and then everything breaks, and I ruined everything. That doesn't really happen like that. So, was there another part to your question? Is that good? Thank you.
もう一つぐらい時間ありますけど、誰か質問がありませんか? All right. Thank you very much, Chris, for coming to speak with us.
Thank you.